Hi, uh, I'm Bree. This is Photolithography on a Budget. So, let's start with waves. What are they and why are they? First off, what are they? They are dynamic perturbations that propagate through the fabric of space-time, which basically means they're just ripples. Some examples: the electromagnetic spectrum, radio waves, visible light, IR/UV light, gravity waves, sound waves, which are pressure waves. So why are they? They're the propagations of disturbances, basically. When there's a disturbance due to the temporally and spatially coherent structure of space-time, as time progresses, so does space. In the case of light waves, they generally travel at the maximum distance per given interval of time that is known to be allowed through space-time, aka c equals 300 million meters a second. And some examples of disturbances that cause waves: electron excitation, such as um, the photoelectric effect has something to do with that. Neutron star collision tends to cause some pretty strong gravity waves. And clapping your hands, sound waves. And waves are the propagations from those disturbances. Some examples: collisions between particles, sound waves, electromagnetic oscillations which travel through space and time, light wave, water being pulled up and down, a wave on, like the ocean or something like that. So photolithography, what is it? The use of light waves to cause reactions in a photoresist on a substrate. A substrate is generally what's being processed, such as a silicon wafer or, in our case, a glass slide. Essentially, it's using light to cast patterns onto photosensitive material to produce physical patterns from the light patterns. And the diagram on the side, or hang on, I'll get to that in a second. So what is photolithography used for? It's generally used as, the main process for making computer chips, although there's a lot more involved, such as, etching and, what is it, like thin layer deposition, like atomic layer deposition, stuff like that. In our case, though, we're going to be using it to make micro lenses. So micro lenses take advantage of the fact that visible light is, a certain wavelength, and with photolithography, you can make physical structures on the scale of those wavelengths. Basically, refraction based on, structures that are smaller than the wavelength. And you can also use it for experimentation, because that's always fun. So the diagram on the right, we see how a silicon substrate with a silicon oxide film, that's the green, the silicon is the blue, or cyan, and you coat it with a photoresist, a very thin layer with a spin coater. And usually it's on the order of a couple microns thick. And in the case of this diagram, they're using a mask. In our case, we're doing maskless photolithography, which we could do very cheaply, relatively speaking. And they basically put the mask over it for masked photolithography, which is generally more we'll get to that in a second. So you expose it, you bake it, and then you develop the photoresist. And then you get this, and then you can use things like hydrofluoric acid to etch the silicon oxide layer. And then you can strip the photoresist, and then you have etched a silicon wafer. So how does it work? Basically, from the light source, you shine the light through the pattern source, or in our case, onto the pattern source, which is a digital micromirror display. I believe that's what DMD stands for. Basically a projector. And the photoresist, the light hits the photoresist and interacts with it, as we'll get to in a minute. So as for sources of patterns, mask-based uses a pre-engineered mask to block light and only allow it to reach specific areas of the substrate. An example of a mask is right here. And it's generally much more expensive. The masks cost a lot of money, especially with the precision they do, especially, when you're getting to like CPU chips and things like that, particularly the more advanced ones. It gets really expensive really quick. but it's simpler and more consistent, generally speaking, using a mask. So maskless doesn't use a mask, instead only casts light rays precisely where it's desired on the substrate. Generally it's more complex, less consistent, but can also be done on the cheap. It can be done for very cheap, and by that I mean using a projector. So, photoresist. Photoresists are generally composed of a resin, a binder that supports adhesion to the substrate during processing. So it's basically that layer that right here, that red is basically the resin, and the UV breaks it down, it breaks it down in this kind of photoresist. So there's two types, but we'll get to that in a second. And then it's able to be dissolved. So then there's also a sensitizer, the photoactive compound that makes it sensitive to light of specific wavelengths. In our case, we're using KL 6000, okay, I'll get to that in a second. But the wavelength that we're looking for is 365 nanometers, just in the UV range. And the solvent, which keeps the photoresist as a liquid, making it fairly simple to use and apply. So that's three things: a resin, a sensitizer, and a solvent. So there's two main types of photoresist, positive and negative. Negative photoresist, the way that negative photoresist works is light toughens the resist and allows the exposed portions of the resist to cling to the substrate for the remainder of processing. Positive photoresist, which is what we'll use, how that works is light weakens the resist, allowing for fairly easy dissolution using a proper solvent, such as TMAH or potassium hydroxide, which is what we're going to use because it's less toxic and much cheaper. So how do you use a photoresist? First, you pre-treat the substrate, especially if positive photoresist layer or substrate or photoresist adhesion can be an issue. So you use something like ammonium hydroxide to help with that. And then you apply the photoresist, which is generally done with a spin coater. So the way that works is basically you put the substrate into the spin coater, and then you put about half a milliliter, in our case, of the photoresist onto the substrate. And then you spin it really, really fast, like a couple thousand RPM. Again, in our case, about 4,000 RPM. And that basically gets you a very even and thin film on the order of microns, less than 10 microns, in our case, on the surface, theoretically speaking at least. And then after you do that, you expose it, and then you develop it. And we would be developing it with potassium hydroxide. So, exposure. We need a light source, a pattern source, and the undeveloped photoresist-treated substrate. So what we're doing is maskless. So we need to prepare the light/pattern source and block it temporarily. So we're going to do that by using a projector and plugging it into a computer and using it like a screen, and then just putting a pattern on the screen, and that's it. And then you place the substrate in the path of the light rays, unblock the light source, and expose it for a designated amount of time, which we'll actually go through the calculations for later. Usually less than a minute. Sometimes, a lot of the times less than half a minute, depending on what you're using. And after that, you develop the photoresist, and that's about it. Unless you're going to do etching and, further processes, which we're not going to be doing in this case. Hi, this is Bree, so I'm just going to show you a quick demo of the stuff I made for this. So, don't mind how messy this place is. That's just kind of, yeah. So, here's the spin coater. This isn't my design, but I did make this. I built it. And modified the design a little bit, but basically, so I'm not actually doing the chemistry right now, so I'm just gonna, so yeah, that display is really dim, but this thing spins pretty fast, and that's where the substrate's gonna be. Spin it, or I'll stop it because that's loud. But yeah, so the substrate we're gonna be using is a 3x1 inch what is it? Glass slide that you usually use for chemistry. And going to be making some micro lenses with it using this. So this is just a projector strapped to a custom mount with a macro lens attached to it with a custom 3D printed adapter. So it's off right now, and before I turn it on, if anyone else ever does anything like this, always make sure you got UV glasses and maybe even something like this if you really want to protect your eyes. So I'm gonna put those on. I'll be right back. Alright, so I got the glasses and the other thing on, so let's boot this up. And you're gonna see in a second, it gets very bright. So bright that actually the camera on my phone can't really handle it very well. So we're not going to be able to see very well. So yeah, anyways, I have this image that I'm going to be using to make a micro lens array. And yeah. So basically you just spin it, put the substrate in here, and expose it for however long. I'm going really quick because my phone doesn't have a lot of storage. And yeah, also those little artifacts are because of the color wheel that's spinning in here, because I haven't gotten around to taking it out, but yeah. So that's basically it for the process. Anyways, yeah, so that's the spin coater. And then the other thing is just a regular mercury arc lamp UHP projector from the mid-2000s. I got that one for like $35 on eBay. You could get them for really cheap. And then you just smack a macro lens on it, like just a regular macro lens off of Amazon or something. And what I did was I 3D printed a custom bracket, designed and 3D printed a bracket for that to securely attach to the projector, and that keeps it from falling off and helps a lot with alignment. And that's basically it, aside from the chemistry, obviously, which the chemistry is a whole other thing, which is basically the chemistry is half of the photolithography, but we're not going to go too in depth into that. At least, well, there's another slide for the chemistry. We'll get there. So here's a diagram I put together of the setup. Definitely not with Microsoft Paint. So this one is based on a design from Sam Zaloof on YouTube. He basically did the same thing, but put it through a microscope objective in order to get on the order of microns. We're not doing that, at least not yet. We're just doing without a microscope. It's a lot easier and simpler for proof of concept, and you don't got to worry about as much about aligning the optics. So here's some calculations. Exposure time. So the approximate energy output of the projector, these types of projectors, specifically the one we're using, the InFocus LP70+, have been measured to output approximately 1,087 lumens of light through a 120 watt UHP lamp. And the lamp is rated to output approximately 3,000 lumens, so we can assume that, this calculation here, 36.2% of the light output from the lamp makes it out of the projector. Although, this kind of cancels out, so we didn't really need to do that calculation, but it's there anyways. And they have an average luminous, so UHP arc lamps, the specific type of projector, or well, light source, that is, has an average luminous efficacy, which is lumens per watt, of approximately 65. So using that and the 1087 lumens or the 3000 times 0.362 lumens, we could get 0.06 watts of output. Hey, so this is Future Brie in post. So there was actually an error with those calculations. I had these flipped. So I flipped them back, and this is the watts. And this is, what is it? The milliwatts per square centimeter that you'll see on the next slide. And this is the final amount in seconds. So either there's an error with my methodology or with some of the data, because I really don't think 0.16 0.16 seconds is enough exposure time. So my primary source, who has done a lot of experimentation, Sam Zalouf, with this method of photolithography using a mercury arc lamp projector and all that, recommends around 20 seconds, and then you know, experimenting, doing a little more, doing a little less, and seeing how it goes. So 0.16 seconds or 0.17 is a little bit off of 20 seconds. So anyways, this is the correct calculation, but I feel like there's an error with the method. Anyways, that's it for the calculations. So the required energy of exposure for the KL6005 positive photoresist, which is what we'll be using, is about 120 millijoules per square centimeter. And that's what we need to achieve in the exposure time. So 120 millijoules per square centimeter is what we need to achieve during the time of exposure. So that's like over time. So that's watts times seconds. That's what a joule is. And the light intensity is 0.06 watts, which is equal to 60 milliwatts, because 0.06 times 1,000 is 60. And the approximate size of the picture at about 40 millimeters distance from the lens, which is what we'll be using, because that's where we could get it focused. That's what we made the focus length of the projector through the use of the macro lens. So I've measured the size of the image to be approximately 5.5 centimeters wide by 4.2 centimeters tall. Multiply those together, you get about 23.1 square centimeters. 60 milliwatts divided by 23.1 square centimeters is approximately 2.6 milliwatts a centimeter squared. And 120 millijoules divided by, 120 millijoules a centimeter squared divided by 2.6 milliwatts a centimeter squared is 46.2 seconds. All the other units just kind of cancel each other out really nicely because of the relationship between joules and watts. You're basically dividing joules and watts. That's all that's going on here. This means that we should leave the photoresist-treated substrate in the path of the light rays for approximately 46.2 seconds. So, the chemistry of photolithography. It's just as much important as the regular non-chemical physics going on with it. In consideration of your time, as well as the fact that this is for a physics course project, not a chemistry course, I won't be going much more into this than I already have so far, for the time being, unless there's questions or anything like that. Relating to the chemistry of photolithography, for the process of doing photolithography, which was the goal of this project, I needed to put together a detailed step-by-step process for carrying out that whole process in a chemistry lab, including things like stoichiometry and solution preparation. Dangerous chemicals are involved, and safety and precaution is required. Always proper PPE, personal protective equipment at all times is essential. Never forget that. So this is where I would be passing around some very basic results around to the class. But I got COVID, and I tested positive the night before I was supposed to do the testing, so that's on hold. So the patterns we're going to be using as test patterns are microlens patterns. I mean, they're not going to be on the order of microns, so we're not going to be seeing visible light refracting. At least that's not the current goal. The current goal is just to use these as test patterns to test the process. And so this is an example of a Fresnel lens, a zone plate Fresnel lens, which is a type of microlens. And here is a link to a video from Huygens Optics. I think that's how you pronounce it. I honestly don't know. Who made the software that I made this image with. Really cool YouTube channel, just like Sam Zalouf. Except Sam Zalouf does more photolithography, I think. I don't know. Anyways, my point is, those guys were pretty much my primary resources for this project, especially Sam Zalouf. This project wouldn't have happened without them. And that's about it. Here's some helpful resources. Special shout out to Rowan Delcourt. I don't know how to pronounce that. He designed the original spin coder and actually responded to my messages online and helped me build my version. And of course, Wikipedia. So anyways, that's it. Thanks for watching / whatever. Yeah. Anyways, thanks. Bye-bye.